All right, good afternoon. This video is for my pre-AP science class for our speed lab that we did earlier in the week. And I know a lot of people have been absent, so I'm making this video for y'all so you can keep up with what we've done in class and get the benefit out of doing that lab even without having to have been there. We did the lab on, I believe it was Wednesday or Thursday. It was Thursday. So if you have been out Thursday, then you'll need to make sure that you get with your group and get the data for that. I'm also going to put on Classroom a list of all of the data tables from each group. So if you were absent, you can find your group and use the data tables from there. I'm going to use the data tables that have been made up. They're not anybody's. They're just made up numbers just to show you how to do each step. So the first is, of course, recording our observations, which I'm going to put in here real quick, and then we'll move on from there. So at zero distance, of course, we had no time because our car was not moving, and we wanted to do at least 2 to 3 trials and then get an average. And so these are my averages. Now, when we do any calculations or anything else in the lab, we will only be using our average times. We will not be using any of the trial times. So please make sure you're aware of that. .8, and that does not look like a 2. 16.6, 21.2, so that gives us an average of 16.4 and 20.9. Okay, so again, when we're doing our calculations and when you're making your graphs, these 2 columns will be the 2 columns that you go by. So the first thing under analysis says to show an example of our calculations for average time. Just to make sure that you know how to do that, of course, you're simply going to add your 3 times together and divide by 3. If you only did 2 trials, you would add them and divide by 2. And of course, time is in seconds. Okay, the next thing it asks us to do is plot a graph of distance versus time, with time being on the x-axis and distance being on the y-axis. And I have these already made out on Excel. We did them on Excel, and then we did them as groups on a large piece of graph paper to hang on the wall. So I'll just give you a brief overview of what should happen, and then I will post, like I said, the data tables and graphs for each group, so you'll just need to download that and glue that into your notebook. So what we have to do is put time on our x-axis in seconds, distance is on our y-axis, and it's measured in meters. Okay, and then if we do that based on our data table, we should have average values from 0 to 21 across the bottom. So we could go over by 5s, 10, 15, 20. Okay, and then going up, we're going from 2 to 10. So we could do 2, 4, 6, 8, 10. And then we would plot each point on the graph. 0, 0, of course, would be down here at the bottom. And then the first point on the graph is 2, at a distance of 2 meters, our time is 4.3 seconds. So we come over here and go up to 2. And then we come over to 8.1 and go up to 4. Now I'm having to estimate where these points are going to be Then I'm going to go over to 12, so that's about right here, and then up 6. Yeah, right here. And then I'm going over to 16 and up 8. And then I'm going over 10, over to 20.9 and up 10. So there's our graph, and we do a line of best fit, and that's what our line should look like. You should definitely see a linear relationship. And everybody showed that. Not everybody's was a very straight line, but everybody's did show a linear relationship. The next question is to find the slope of the line. And we're going to find the slope manually. Now, when I give you the equation that I've done through Excel, or the graph that I've done through Excel, it gives you an equation. And it gives you slope then. But we're going to find slope the old-fashioned way as well, which is rise over run. So slope, remember, is y2 minus y1 over x2 minus x1. But in our cases, it's going to be the distances over times. So we're going to pick 2 points off of our table, and we're going to subtract those and get our slope. So let's do 8 minus 0 for the meters, and 16.4 corresponds with the 8-meter distance, minus 0 for the seconds, gives me 0.49 seconds. That is my slope. Okay, now it's also, since we're doing distance over time, slope is also velocity. So velocity V is equal to distance divided by time. That was in your notes. And that's also the slope of this line. That's how we get velocity. So anytime you have a distance versus time graph, slope equals velocity, always. Okay, conclusion questions. Write a general statement explaining how you found the speed of the car from your data. How we found it, we just found the slope of our line in a distance versus time graph. What is the mathematical relationship between distance versus and time? It is a linear relationship. What does the slope of your graph represent? Slope equals velocity. Suppose your hallway is 50 meters long. How much time would it take for the car to travel the entire length of your hallway? Well, we're going to go back to that equation of V equals D over T. We know the distance is 50. We know our velocity. Now, everybody's is going to be different, of course. We know our velocity, and we're going to find time. So our velocity that we found earlier was 4.9 meters per second. We found that back in number 3 of the analysis questions. And our distance is 50 meters, so we are looking for time. Time is in the denominator. We don't want it there, so to get it out of the denominator so we can solve for it, we need to multiply both sides by t. And then I'm going to divide both sides by 0.49 to give me my time. Time will cancel out, or the meters will cancel out and leave me with time of 100 seconds. And significant figures, you nearly only need one significant figure. No matter what your velocity is, you're only going to need one significant figure because 50 only has one. Number 5, how would the car travel, how far would the car travel in 3 minutes? Same type of thing. We're going to use the same equation, but this time we know time and we know velocity, and we are looking for distance. Okay, so velocity again, same thing we had before, 0.49 meters per second, and everybody's will be different on that. Distance is what we're looking for. Our time is 3 minutes, which we don't want minutes because velocity is measured in meters per second. So we're going to need to change that minutes to seconds. Okay, 3 times 60 would be 180 seconds. To get d by itself, I'm going to have to multiply both sides by 180. So d is going to equal 180 times 0.49, which, and again, I only want one significant figure. That's going to be 90 seconds. Question number 6. Another student group has a car that will move twice as fast as your car. Predict the time it will take for their car to cover half of the 10-meter course. Okay, so again, we're looking for time. Velocity is always equal to distance over time, but this time I'm looking for time. So t is equal to the distance divided by velocity. All right, so for this, we say we're covering half the course, which would be 5 meters, and our car is going twice as fast. All right, if it was 0.49 meters per second to begin with, then that times 2 is about 1 meter per second. So our time would be 5 seconds. So that's all we're doing with that one. Plugging into V equals D over T, rearranging it, and putting in our numbers. Number 7 says, discuss a reasonable source of error in determining the speed of your car. Explain how this error increases or decreases your value for speed. Just some possibilities for human error is not starting and stopping on time. The car not going in a straight line. Both of those could be possible human errors. If we didn't start and stop on time, then our time value is not going to be correct. And if it's not going in a straight line, then we're actually going to have a bigger distance than we should. So that will affect distance equals velocity over time. So if this number were to increase, that might make our velocity slower. If this number were to increase, it might make our velocity faster. So, all right, let's move on. Number 8 says sketch a graph of speed versus time for your car on the graph provided. Now, speed, to get the speed at each point so we can do a graph, we are going to need to go back to our original data table and again divide distance by time. And what you'll find at each point is that your velocity is pretty much constant. It's pretty much the same number. Every single time we divide that out, we get something around 0.49 meters per second. So if we graph that, you are going to have at every time interval okay, so we have a constant velocity of 0.49 meters per second. So when we graph that, we would have 0. Here is our 5 seconds. Here's 10, 15, and 20. And our velocity is going to be about the same number every single time. So I'm going to go up by, let's see, let's do 0.1, 0.2, 0.3, 0.4, 0.5, whoops, 0.6. all of my velocities, if you take each data point in your table, distance divided by time at each one of those intervals, you'll get approximately the same number. It might be slightly off here or there. But it's for mine, it's 0.49, which is going to fall right through here. So you would just get a horizontal line, okay? And this horizontal line, of course, would then have a slope equal to 0. That means there is no acceleration. You're going at a constant velocity. Your velocity is not changing. And that's what we expect. We would not expect our velocity to change in this situation. What quantity does the area under the speed versus time graph represent? From your graph, what is its value? Okay, the area under the curve represents the displacement. Or the distance. And what is that? It would be the slope, velocity. I'm sorry, not the slope. I said that wrong. It would be the velocity, 0.49 meters per second, times the time of 20 seconds, which is 10 meters, which is how long our track was. If you remember, our track was set out to be 10 meters long. When they talk about area under the graph, we mean the literal area, length times width, velocity. So the area would equal velocity times time. Our velocity went up to 0.5 meters. And our time went out to 20 seconds. So that's why we multiply those two things together, and we get 10 meters, which is our distance, or we call that our displacement. Okay, and that is it. So I hope this is helpful to you. We will probably grade this lab next Wednesday. Somewhere in there. So hope you have a great weekend. Bye.